Okay, welcome to this FMSP online revision video. This video is on OCR FP3 on the topic of groups. We'll start by looking at the specification statements and then go on to looking at some exam questions. So, in terms of groups, the main thing you need to know is what a group is, which is a set of elements, objects, together with a binary operation, often something like multiplication or times, or it can be any operation between two things. That's what binary means. And the crucial thing is that the elements are closed, associative, that there's an identity and an inverse. Now, three of these are pretty easy. Closed just means if you apply your operation, say it's multiplication, to any two objects in the group, you get another one in the group. Identity means there's an object a bit like 1 in multiplication or 0 in addition, where you apply the identity to the object, you get the object itself. And inverse says that there is an object, another object in the group, so if you apply the operation to these two, it takes you back to the identity. And you can think of this very much like the inverse of 3 in multiplication is a third, because 3 times a third is 1, which is the identity. The key one that's maybe slightly new to you is the idea of associativity. So an operation is associative if I'll use multiplication here, it can be any operation, A times B times C, so apply it to this pair and then apply the outcome to this, is the same as if I applied it to the second two this way. And you can see under integers, multiplication is associative. Probably better say under rational numbers there. So you can think of this in terms of three friends. So the order they associate with each other doesn't matter. It doesn't matter if these two friends associate with each other first and then associate with this other one, or likewise if these two have associated with each other first and then they associate with this one. So these four properties must hold. You should then, given a group, be able to show whether these four properties hold and it is a group, or in some cases you might be asked why something isn't a group because one of these is failing. Use standard algebra to establish properties within groups. In easy cases, we'll have a look at this, and there's a mention here of the idea of commutativity, which is a group, an operation, and a group is commutative if A cross B equals B cross A. This doesn't have to hold for something to be a group. If this does hold, then the group is commutative. And you can think about this, I tend to think of it as commuting from home to work is the same as commuting from work to home if all I'm interested in is the distance. So I can say the distance of commuting is commutative because it doesn't matter whether I'm talking about home to work or work to home. You should know the meaning of the term order. So the order is, for a group, if it's a finite group, it's the number of elements. If it's an individual element in the group, it's what power, and power in terms of how many times do you apply the operation to get back to the identity. We'll look at that in a particular exam question in a minute. Might make more sense then. And then there's quite a bit of stuff on types of groups and subgroups. So a subgroup is literally a subset of a group where our four properties of closed, associative, identity and inverse still hold if I take a subset. And there's this idea of a proper subgroup, that obviously there is the trivial case for a group that the whole group itself or the identity element are groups, but they're trivial and we ignore them because they're not that interesting. So we talk about proper subgroups. And you should know Lagrange's theorem concerning the order of a subgroup of a finite group, which is that it must divide it. So if you want to find subgroups of a group of order 9, the only proper subgroups there could have order 3. You've then got a couple of things that and one of them we'll look at in detail with an exam question, is this idea of a cyclic group, and show familiarity with the structure of finite groups up to order 7. So a cyclic group is whereby multiplying by each object in turn takes you through the possible values in a group. So the group of order 3 is cyclic because it's got 3 elements, E, A and B, which can be written as A squared. So a times a is a squared, and a times a times a times a squared takes me back to e, the identity. And that's a cyclic group because multiplying by a just keeps moving me along these. What you need to know, and we'll look at in detail, is that for groups of order 2 and 6, there are groups of order 4 and 6, there are non-cyclic subgroups. Everything else up to order 7 is cyclic, apart from your two special cases of 4 and 6, where there's both a cyclic and a non-cyclic one. And finally, isomorphism is just a long way of saying two groups are the same, is if you can construct a table for one and construct a table for the other, and the position of the elements in the table are the same. In other words, applying the operation to the objects would give you the same result, and that so in some sense those groups are the same group, and we use isomorphism for that. So we'll start with an exam question. This one's on a infinite group, and this is really looking at a couple of the properties in terms of, are they closed, and is there an identity, and is there an inverse, and then we'll take a look at associativity in a separate question. So I'm going to read through the question to begin with before I have a go at it. Here it says H denotes a set of numbers of the form a plus b root 5, where a and b are rational, and the numbers are combined under multiplication. So we want to show that the product of any two members of H is a member of H. You're then given a and b are non-zero, and that H forms a group under multiplication, and you're asked to state the identity element of the group, then find the inverse, and part 4, with reference to your answer to part 3, state a property of the number 5 which ensures that every number in the group has an inverse. So really this is just looking at an infinite group, and does it have the closed associative and inverse properties? Closed associate, closed inverse and identity properties. So part 1. Show the product of any two members of H is a member of H. So if I take any two members, I could have a plus b root 5, and I could have another one with another two rational numbers, c plus d root 5, and I'm multiplying them, it's the product. So the product of those two expressions is going to be ac and also another rational number, which is 5 times bd, just by multiplying my two root 5s together. I'm then going to have two terms in root 5. I've got AD root 5 and BC root 5. So I've got AD plus BC root 5. Lastly then, just to make sure I get all the marks here, I want to show that it's a member of H. It says where these two things are rational, so I just want to say these are rational. So it's in H. In part 2, I want to state the identity element of the group. In other words, and it's only one mark, what do I multiply a plus b root 5 by to get a plus b root 5? Well, the identity here is just 1. Pretty straightforward, single mark for that. Looking at parts 3 and 4 then. In part 3 we're asked to find the inverse of a plus b root 5. Well, we now know what the identity is, so what we want to do is take a plus b root 5 and multiply it by something that's also in the group that gives me my identity. So I've got my inverse is going to be 1 over a plus b root 5, and then we're just back into a bit of AS core really. How do we rationalise the denominator? Well, multiply by a minus b root 5 over a minus b root 5. I'm going to get a common denominator here of a squared minus 5b squared. My first term then is going to be a over that, and my term in root 5 is going to be minus b over a squared minus 5b squared root 5. Lastly then, 1 mark, state a property of the number 5 which ensures that every number in the group has an inverse. So in other words, we're being asked, does this always exist? Well, this always exists provided a squared minus 5b squared isn't 0. Could that happen? Could we have a squared minus 5b squared is 0? That would leave us to a squared over b squared equals 5. So we've got a over b is equal to root 5, but that's not possible where these are rational numbers because root 5 is not rational. So that means we're never going to get 0 on the denominator here, and the inverse will always exist. So let's take a quick look at how the marks will be awarded for this question. On the first part here, there's a method mark for multiplying out, and then an accuracy mark for getting an answer that clearly shows that they are rational. Part 2, a straightforward statement mark, B1. Part 3, again, a method mark for a suitable method. There are alternatives, but this one's probably similar to what you've been doing in, say, AS Core, and then an accuracy mark for the correct answer there, and then finally a statement mark here for identifying your property of root 5. So that's looked at closed identity and inverse properties. Let's take a look at how you might be asked questions based on the associative property of a group. So in this question, you're told a multiplicative group with identity E contains distinct elements A and R with the properties R to the 6 is E and AR is R to the 5A. You're asked to prove that RAR is A and prove by induction or otherwise that Rn A R to the n is A for all positive integers n. So this is going to be based on putting things together in this in terms of the associative property of groups. So I'm going to start to prove this thing. I'm sure you've done this technique before. A standard way to prove an equation holds is to start with the left hand side and get through to get the right hand side. So I'm going to say RAR is equal to, now what do I know? Well, I know AR is R to the 5A. So I've got, put that in the wrong place, I've got R times by R to the 5A. Now I've got to be very careful, and I want to show the examiner here that I understand associativity. So now I'm going to put these two together in this order and say this, keeping the order there fixed, but I can do any pair together at any one time. So I've got R to the 6 times A. R to the 6 is E, so I've got the identity element times A, which is A. Part 2. Prove by induction or otherwise that R to the n A, R to the n is A. Well, I may as well try induction because that's what it's suggesting there. So, going back to FP1 stuff, is this true for n equals 1? And I've got R to the 1, A, R to the 1 is RAR, which is A by part 1. We've already proved that. Then, in my standard way of writing out induction, I'm going to say assume it's true for n equals k. In other words, R to the k, A, R to the k does equal A. And then I'm going to look at R to the k plus 1, A, R to the k plus 1. Well, I can separate this out as R times by R to the k times by A, and separate this out as R to the k times by R. So in the middle I've got this thing here, which I know is A. So that is R A R. and finally RAR is A, and that is A. So true for all positive integers n. Let's take a quick look at the mark scheme for this question. We've got a method mark and an answer mark here. Then there's a statement mark of doing your n equals 1 case correct by part 1. A method mark for a correct inductive process here. An accuracy mark for getting to this line here of splitting up the statement in the k plus 1th case, and a final accuracy mark for following the induction through to the end and getting the correct answer. So that's an example of the sort of thing you might be asked in terms of associativity. We'll finish by an exam question that really looks at subgroups and cyclic groups and cyclic subgroups. So, in this question, you're told Q is a multiplicative group of order 12. Two elements of Q are A and R, and it's given that R has order 6 and A squared is R cubed, and you're asked to find the orders of the elements A squared, A cubed, R squared. You're then, in the second part, given the table with the order of each of the elements, told that G and H are non-cyclic groups of order 4 and 6 respectively, and asked to construct two tables similar to the one above, show the number of elements with each possible order for the groups G and H, hence explain why there are no non-cyclic proper subgroups of Q. So this first part here is really just looking at orders of elements, and it's the second part when we're going to get into the whole subgroup and cyclic nature. So let's start with the first part then. We want to find the orders of the elements A squared, A cubed, and R squared. Well, I know that A squared is R cubed, so A to the 4 is R to the 6, and R has order 6, so R6 equals E. So therefore A squared, A to the 4 will be the same as R6, so A has got order 4. You don't need to write this, but what I basically have done to find that out is worked out what power of E will give me the identity element. A squared is a bit easier. R cubed squared is the same as A2 squared. R cubed squared is 6, which is the identity. So this has got order 2, so this has got order 2. A cube's a bit trickier, so we could have a quick think then. We've got A cubed, which doesn't equal E, A cubed squared, which is A to the 6, A to the 4 is E, so this is A2, still not E. We've got A cubed to the 9, not sure what that is, but it's certainly not going to be E. A cubed to the 4 is the same as A4 cubed, so that is going to be A. Or you could look at it as being this one squared. So A cubed has got order 4. And finally, R squared, what power would we raise this to? Well, if we cube this, it's the same as 6, so this has got order 3. Right, that's looking very basically at orders of elements in a very abstract case. You're then told that the order of the individual elements in this group of order 12 is as follows. There's 1, the identity element, with order 1, 2 that are self-inverse, 1 that's self-inverse, 2 where they're order 3, 6 of order 4, and 2 of order 6. You're told G and H are the non-cyclic groups of order 4 and 6 respectively. So these are the two ones I was mentioning at the beginning that you need to know. Everything else up to 7 is cyclic, apart from in 4 and 6 there's two alternatives. You can either have a cyclic group of order 4, Or you could have a group where everything is its own inverse. If everything is its own inverse, we're going to have a table where we've got order and the number. Well, there's always going to be one object that is the inverse, so there's always going to be one object of order 1. If everything else in the group is self-inverse, everything else has got order 2, so there are 3 elements of order 2, and these are your 4 elements in the group. If you're unfamiliar with this, have a look back at your notes or your textbook to find what the non-cyclic group of order 4 looks like and confirm that it would have this table. Similarly, for non-cyclic group of order 6, we can have the following orders and the number of elements. Again, there's going to be one of order 1, the identity. You then have a pair of elements that together give you a cyclic group of order 3, and 3 elements that are self-inverse. So there's 3 elements with order 2 and 2 elements with order 3. So this and those together make your cyclic subgroup of order 3, or your only group of order 3, and these 3 are self-inverse. Again, if you're unsure on this, go back to your notes. You should know this subgroup and you should be able to draw out a table for it, or draw out this type of table for it. So look for that in your notes if you're unsure on that. So we're then asked to construct 2 tables similar to one above to show number of elements, possible groups, for order for the groups G and H, which are here, and from these explain why there are no cyclic proper subgroups of Q. So the first thing to say is, if there were proper subgroups of Q, the possible orders are, well, this is Lagrange's theorem. The big group has got order 12, so it would have it's the numbers that divide 12 other than 1 and 12 because they're trivial. The proper ones could be 2, 3, 4 or 6. Now we know here that 2 and 3, those groups are cyclic, so the only possibilities for a non-cyclic subgroup are 4 or 6. But when we look, to get a non-cyclic group, we'd either have to have 3 elements of order 2 here or 3 elements of order 2 here. But our original group only had 1 element of order 2. It only had 1 self-inverse. So we can't find a subset of this that could make up these tables. But Q has only 1 element of order 2 and these need 3, these 2 here. So let's take a look at the marks for this question then. So in the first question here, it's a method mark for evidence of correct working in terms of finding the orders. These sort of notes the right hand side are very useful to the examiner, and then a further 2 accuracy marks if all 3 of these are correct, 1 accuracy mark for at least 1 correct, and finally a statement here of mark for that. In the second part of the question, there's a method mark which is evidenced by getting the top line of the tables correct. If you'd put a 4 and a 0 or a 3 and a 4 and a 0, that would still be correct. You wouldn't lose marks for that. It's just not necessary. And then an accuracy mark for each of these. And then 2 marks here, 1 for clearly identifying that the proper subgroups of order Q must have order 2, 3, 4 or 6. That's Lagrange's theorem. And then finally a statement mark there for a correct answer. So that finishes this video. Please look online for other videos for OCR, FP3 and for other units as well.